So we're going to look at Riemann sums here and just kind of introduce the idea. And a Riemann sum is named after the guy who came up with these, Riemann. And this is the sigma notation form of adding up the area of a lot of rectangles, which was the idea that we were looking at in section 5.1. We were approximating the area underneath a function's curve or a function's graph by adding up the areas of a bunch of little rectangles in there, because the area of a rectangle is pretty easy to compute. And so we can get reasonable estimates for the area underneath the curve that way. So to set this up, let's give ourselves a little graph here. All right, something nice and generic. All right, your graph might look a little different. That's fine. You're just making some sort of curve. And we're going to look at the area underneath this curve from A to B. All right. So that would be all of the area underneath that curvy function graph between the two dashed lines. Okay. So from section 1, we saw that we could cut up this area into a bunch of rectangles. We looked at what happened with different numbers of rectangles. It would get more accurate the more rectangles that you involve here. And yeah, in the chat here, there's a question on whether Riemann sums include a delta, and they do, yeah, a change in some different values. So yes, this is good. That's actually going to be the change in the x direction, which is what we're about to put on the graph here. So if you cut up your interval from A to B into a bunch of little rectangles, each one involves a tiny change in x. Like the width of each rectangle is going to be some sort of delta x term. All right. Like this, if this is your first rectangle, up there. All right, you might call that like the change in x sub 1 for first rectangle. And then this would be like the delta x sub 2 change in x for the second rectangle, that type of thing. Okay, yeah, so this is sounding familiar to you. Nice. And so you're going to have however many rectangles you want in here. I was trying not to make these look any particular size because I just want to keep it generic. But the idea here is that you're going to cut this into different rectangles, and this is called partitioning. So partition into rectangles, and that's what causes that little delta x term. Okay, and in practical terms, delta x actually doesn't have to be exactly the same for each rectangle. In practical applications, sometimes you might be able to get away with using a wider delta x for one rectangle. And then if things are changing faster, you might want to use some smaller rectangles in areas like that. But most of the time for this class, we'll just consider them all to be the same size. So delta x will be the same for each rectangle. But yeah, we want to pull out one of these rectangles so we can look at it and see what the area is. And that's what we're going to do here. Area of the, we'll say this is the kth rectangle. And we're calling it kth there, like it could be the 15th rectangle or the 27th rectangle or something. And the idea here is that it's just a very generic sample rectangle that you're pulling out of all of those rectangles that you've used. Okay, generic sample rectangle. Okay, so if we sketch just like a super generic little rectangle here. All right, it's got that width to it. of delta x, like you were thinking of. And since it's the kth rectangle, we'll call that delta x sub k. And then the height of that rectangle, if you think back to section 5.1, there were a couple different ways that we could set the height of the rectangle. And it was all based on a function value, because remember we would like go up from maybe one endpoint or the other, left endpoint, right endpoint, and that would give us the height up here by using the function value. So this is the function value of a selected point. So yeah, we could use right endpoints or left endpoints or midpoints were the main three that we looked at in section 5.1. So left, right, and middle. Okay. And so for this, to keep it nice and generic, we'll just call the point that we're using to set the function value or set the height of the rectangle, we'll call the selected points just some value of c sub k. It's some constant number within that rectangle. So that's just showing that there's different options here. Okay. Just making everything like as generic as possible. Okay. So if we've set the width to be delta x sub k, and then we're using the height of the rectangle as the function value at c sub k, then we can find the area of this rectangle. So area, and I'm running out of room a little bit there. The area for that kth rectangle is just going to be the length or height f of ck times the width, which is delta x sub k. And so that is going to be really helpful for us because that will give us the area of one little rectangle. So like here on the first rectangle, you'd have A1 and then A2, and then however many rectangles you end up using. We're going to take that and add up the areas of n little rectangles underneath there to get the area of our curve as a Riemann sum. So here's the basic idea of a Riemann sum. The book calls this S sub P. Don't worry about that notation too much. The main thing to know is this right-hand side. We're getting the summation from k equals 1 to n. So starting with your first rectangle and then adding up all the way to your n rectangles there. And on each rectangle, we're going to use its little area, a sub k. So we'll take that f of c sub k times delta x sub k. And that would give us the area underneath our curve. And that's what's called a Riemann sum. So yeah, I'll go ahead and pause right there because that gives us the basic idea. But yeah, we're going to expand on this in the next video.